In this video, I'm going to be doing a test preview for the test that goes along with the second half of Unit 3 in Chemistry 1 College Prep, or CP. Now, if you're watching this video, it's because I am not here, and I know this is kind of a wild and crazy looking shirt, but it is Hawaii Day on the day that I'm actually recording this video. If I'm not here, then that means you must have a substitute teacher, and I expect the best behavior from you when you have a substitute teacher. Now, when this review is taking place, I also expect that you are going to be watching intently, you're going to be taking notes, and you're going to be doing your very best to pass this test with an A. There is no excuse for not taking this test unless you were absent yesterday, for example. If you choose not to take this test, you better have a very good, a very valid reason, or it's just going to be entered as a 0. Also, you know that during testing, you are to have no communication amongst yourselves while anybody in the room is still taking the test. If you are on your phone, if you are giving looks at somebody else, if you are passing notes, the substitute is going to leave me a note and I will simply put in a 0 for your grade. No communication. When you finish that, you know that during the test you keep your eyes on your desk and only on your desk. You can have a set of yellow test references. You can have a standalone calculator. You need a pencil to take this test. Nothing else is to be on your desk. If the substitute sees you take out something else or look at something else, they're going to leave me a note. I'm just going to record a 0 in the grade book. So we all know this, but I just want to make sure you're clear with this right up front. So watch this preview video carefully, and as soon as this video is finished, then the substitute can give you your tests, and that is all that's going to be required in this class period. All right, this is the Unit 3B test review, or really perhaps we should call it the preview for CP chemistry. All right, and the three things that I'm going to be talking about here are determining if a compound is ionic or covalent. We're going to use orbital notation and electron dots to show how compounds might combine, and there's two subcategories. We're going to do this for covalent and ionic. So you first have to figure out if a compound is ionic or covalent to determine how this is going to be done. And lastly, we're going to illustrate the shape of three simple molecules. So let's start out by determining if a compound is ionic or covalent. If I have a formula for a compound, there are two ways of determining if a compound is ionic. One of those ways, and these don't work independent of each other. Either one of these two things will identify an ionic compound. Okay, either you're going to have an ionic compound when you have a combination of a metal and a nonmetal, or if the compound contains a polyatomic ion. All right, so let's start with this one, metal or nonmetal. On the periodic table, there's this stair step on your big periodic table. Anything that's on this side of the periodic table, any element from here over this way, is going to be a metal. So copper, nickel, palladium, silver, all of those are metals. Okay. Now some of the elements right along this stair step are called metalloids, but that doesn't affect how we're going to use them for determining how the bonding is going to occur. Aluminum is the only element that borders the stair step that is a metal all the time. Okay, boron is a metal sometimes and a non-metal sometimes. That's why we call it a metalloid. Silicon is a metalloid. germanium, arsenic, antimony, tellurium, polonium, astatine. Those are all metalloids. But for the purposes of what we're doing right now, if it's on the upper side of that stair step, it's a nonmetal. If it's to the left down here, it's a metal. Okay? So if I have a combination of these two elements, I'm going to look on the periodic table and see if I can find them. And I'm seeing that copper is a metal and chlorine is a nonmetal. If I have a name of a compound, I have to interpret whether I have a metal and a nonmetal or not. Well, chromium is right here. It's a metal. Sulfide comes from sulfur. Sulfide comes from sulfur, and it's right here. So it's a metal and a nonmetal. And as far as determining if I have a metal or not, only metals are going to have Roman numerals. And only metals are going to have Roman numerals when they have more than one kind of oxidation number. So magnesium, for example, here only has one kind of oxidation number, a 2+. But chromium has 5 different possible oxidation numbers. So this metal has to have a Roman numeral, but magnesium, when you name it, will not. So that's the way you're going to do it when you have a formula and when you have the name of a compound. Now, if I have something like this, let's see, how about we say all right, any of the names of chemicals that have ATE endings, when the last name ends with an ATE, well, that tells you almost automatically that you've got a polyatomic ion. If you look on the common ions list in your test references, the 8 endings on here all tell you have polyatomic ions. Now, there are some polyatomic ions that don't have 8 endings, but they're either going to have an 8 ending or they might have an ite ending. Oop, let's make that an I. So any compound name that has an 8 ending, where the second word has an 8 ending or an ite ending, that's going to tell you that it has a polyatomic ion. That's just automatic. Okay. Now there are a few polyatomic ion names that don't have 8 endings or ite endings. Hydroxide is one you must know just from memory. OH is a polyatomic ion that does not have an 8 or ite ending. Cyanide is another common one that has no 8 or ite ending, but it is a polyatomic ion. Almost all the others do. So that's going to tell you have a polyatomic ion. It's going to tell you have an ionic compound. Okay. Let's see. Let's do this. Let's write down. Oh, how about? Okay. If I have a compound name, or a compound formula rather, with more than 2 elements, this has 1, 2, 3, 4 different elements. This is why it's so important to capitalize the first letter and make sure it's very clearly a capital first letter, and have a clearly lowercase second letter when you write an element symbol. If you have all things that look like all capital letters, we can't tell what element you're looking at. Capital C little u is copper. Capital C capital U is carbon and uranium. So you need to make sure you're very careful about that. But this has 1, 2, 3, 4 elements. If you have more than 2 elements, you want to look on this list of common ions and try to figure out what part of this formula is a polyatomic ion. Well, I'm looking right here at something called phthalate, and I can see that phthalate is C8H4O4. C8H4O4. So I have a polyatomic ion. That tells me I have an ionic compound. Now, for what we're doing in this half of Unit 3. We're really only worried about the metal-nonmetal combinations that make an ionic compound. These are more complex than we want to get into in this class. We're just going to be looking at how to combine these when we're using orbital notation or electron configurations. Now let's look at covalent compounds. Covalent compounds fall into two categories. You've got the non-organic and you have the organic. Okay? Non-organic compounds will be all non-metals. So if I have N2O5, I can go to the periodic table and I can see that nitrogen and oxygen are both, from the stair step up to the right, those are both non-metals, so I have a covalent compound. If I have a name like Phosphorus Pentachloride, okay, phosphorus is a nonmetal. Chloride comes from chlorine, so those are both nonmetals. Also, the prefix penta is only used when you have when you have covalent compounds. Now, the organic compounds use similar prefixes. You have meth, meaning one carbon, eth, ETH, meaning two carbons. Meth, eth, prop means there's three carbons. Bute is 4. Once you get to 5, they look very similar to the prefixes we use for non-organic covalent. But instead of penta, it's pent. So a pentane means I have a carbon chain with 5 carbons in it. Okay? If I have C4H10, this is an indication I have 4 carbons in the chain, and that's a bute prefix for 4 carbons. This would be butane. All right. For figuring out how compounds are going to go together, we're only going to be working with the very simplest of compounds. Okay? So we're going to use orbital notation and electron configurations to show how compounds might combine, and we're going to do this for both organic and covalent. So let's first put together magnesium and fluorine. All right, I'm going to put together a compound that contains both magnesium and fluorine, and I'm going to use orbital notation and I'm going to use electron dots. Okay, well, first I need to know, is this an organic or a covalent compound? Well, magnesium is here and fluorine is over here, so this is a metal-non-metal combination, so we must have an ionic compound. This must be ionic. Okay, so we're going to use the ionic system where electrons are being moved from the metal to the non-metal. So let's first write the orbital notation for magnesium. So we have a capital Mg. Now be careful, magnesium is Mg, but manganese is Mn. So be very careful that you figure out exactly what the symbol is and what the name is for these. So magnesium is located here, and we're going to fill up all of the first energy level, all the second energy level, and 2 electrons in the third. So to fill up the first energy level, that just has 2 electrons, and those are going to be in 1s. In the second energy level, you have both s and p orbitals. So 2s, 2p. And we're going to fill them completely up, 1, 2 here, 1 in each box, and come back and pair up these in 2p. And when we get to the third energy level, we only need 1 box because there's only 2 electrons. For magnesium, 1, 2. We're counting across to find the number of electrons we need in a primary level. So that's magnesium. And then fluorine is located right here. And we're going to fill up the first level and fill up the second level with -1. So we're going to almost fill it up, but not quite. So 1s, the first energy level 1 is full. The first energy level has only an S sublevel, and we need 2 electrons there. So we get to the second energy level, 2s. These elements over here in the first 2 columns represent filling up of the S sublevel. So there's 2 electrons there because we're going to go through that all the way over here. And over here in this P sublevel region, this last 6 columns of elements is the P sublevel region. Helium really belongs over here in this SPDF way of arranging the periodic table. In this P sublevel region, we have 1, 2, 3, 4, 5 elements. We're going to need 5 electrons in that P sublevel. So in 2p, we always have 3 orbitals. 1, 2, 3, 4, 5. Okay? So that's the orbital notation for magnesium. That's the orbital notation for fluorine. What we need to do, though, is to eliminate all the electrons from the orbital notation's highest energy level for magnesium, for the metal. Metals lose electrons, and we want to get rid of all the electrons from the highest energy level. So this 1 electron here is going to drop down here. Okay? So 1 of those electrons is now gone, but that doesn't completely eliminate all the electrons in that highest energy level. 3 is the highest energy level. So the only way we can get rid of another one, we can't just toss it away. We have to have a place for it to go, and the place it's going to go to is fluorine, and so I need another fluorine atom. And now this electron is going to go over here and put it in there. And I'll take that out to make it complete. Take this electron out of magnesium to make this complete. Okay? Now, since magnesium originally had 12 protons and 12 electrons, but we removed 2 electrons, now we have 2 more protons than electrons. Protons are positively charged, electrons are negatively charged. So we have 2 more positive charged particles than the negatively charged particles. So magnesium is going to have a 2+ charge. Each of these fluorines have a 1 negative charge because we added an extra electron. They originally fluorines had 9 protons and 9 electrons. We added an extra electron. Now we've got 9 protons and 10 electrons. The electrons are negative, protons are positive. We have 1 more negatively charged particle in fluorine, and then you have positive particles, so the charge on the fluorine is a 1 negative. If you don't finish that out with the charge, it's not complete. All right, so that's how you write orbital notation and show how ions are going to form in an ionic compound. Now let's use electron dots to do the same thing. Well, magnesium originally had 2 electrons in its highest energy level. The electron dots uses dots to show electrons in the valence level only. So we don't look at these electrons. We're not representing these electrons in an electron dot formula, only those in the highest energy level. That highest energy level is called the valence level. So I'll put 1, 2 dots there, 1 on each of 2 sides of an imaginary square. Now fluorine then, in its highest energy level, has 7 electrons, or did before we put this one here. So we had 2 electrons in 2s. The second energy level, this coefficient 2 here, is the highest energy level. So both s and p electrons in 2 are in the highest energy level. So fluorine has 2 here and 5 here, making a total of 7 electrons in that highest energy level. That highest energy level is called the valence level. So we're going to start by putting 1, 2, 3, 4, 1 dot on each of the 4 sides, and pair up for 3 more to make a total of 7 electron dots to have an electron dot formula for fluorine. So we have an electron dot formula for magnesium and fluorine. Magnesium wants to get rid of all the electrons in its outer energy level. That's what these dots represent, the electrons in the outer energy level. Up here, we got rid of both of them out of the box. Here, when I get rid of them, I will have no electron dots around the metal. So one of these electrons can move over here, okay, but I still have to get rid of another electron. So I need another fluorine. So this electron now is going to move over here to show what is the result of all that, I need another drawing. All right? So it's kind of like we have a comic book, and we're going to make this one panel, and this is the second panel. And the second panel will have magnesium here with no electron dots. And since it lost 2 electron dots, representing the loss of 2 electrons, it has a 2+ charge. The fluorine gained an electron. And since it gained an electron, it's going to have a negative charge. But if I leave that negative right there, it's not clear that that negative applies to the whole monoatomic anion. It may, just looking at it, you wouldn't know that it doesn't apply to maybe this electron. So to make sure that it's clear it applies to the whole monoatomic anion, we're going to put a bracket around it so that the negative charge is outside that. Now, we have 2 of these fluorines, and we can show that in one of 2 ways. We can either show it by drawing it twice, or we can show it by writing out, let's do this, writing it out one time, but put a coefficient 2 in front of it. So that shows I have 1 of these and 2 of these. Either way, we use this, we see that we have 1 magnesium and 2 fluorines. 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 So the formula is MgF subscript 2. In the first half of this unit, we would have looked over on the periodic table with charge numbers, and we would have seen that magnesium has a 2+ charge, and fluorine only has 1 kind of negative charge. And so to balance the charges, we would have needed 2 of those. We put them together, we'll get the same formula, MgF2. So whether we were doing this, balancing this formula from the first half of this unit or the second half of this unit, we're going to get the same formula. This helps you to see exactly how it is that these electrons can move, and technically they may not actually be moving, but it gives you the idea of how metals lose electrons, nonmetals gain electrons, and that you balance out the charges by electrons. Now, let's do this. Let's do a combination where we're going to combine, let's see here, how about nitrogen and chlorine. So here we're putting magnesium and fluorine together. Now we're putting nitrogen and chlorine together. Nitrogen has 5 valence electrons. 2 electrons from the S sublevel, 1, 2. 3 electrons from the P sublevel, 1, 2, 3, for a total of 5 valence electrons. Let's first do this with orbital notation. Actually, I probably need to move this down a bit in order to have more room to do it. I'm going to need more space. And you may find when you're doing it that you need to move yours around. So maybe you want to do it on a separate sheet of paper and then transfer it to your test or whatever. But here's, we'll put nitrogen down here, and I'm going to write its orbital notation. Okay, and I want to combine all 3 of these electrons with an orbital notation for chlorine. Well, let's just sort of put chlorine up here for a second and look at it. Chlorine looks like this, and don't shy away from writing out things out to the side to kind of figure out what it looks like before you start. Oh, that's 3S. Sorry. All right, so what I need then, well, actually I put an extra electron in here. I need to have one less electron. Try to get that to look more like a 3 there. All right, so I need to be able to overlap. Since this is two nonmetals, let's look at where that is. Both of these are located over here, above this stair step to the right. So they're both nonmetals. We're going to share electrons now. Okay, so to share electrons, then I need to actually share not just the electrons in this last orbital and one of these three. I also need to share the orbital itself. So I need to fit this orbital and one of these three together. Okay, so what I'm going to do is I'm going to make chlorine fit right in over here. I'm really running out of space here. Okay. So I'm going to erase part of this name of chlorine here so I can get everything on here. You just have to know that's what it was originally to get it all done here. Okay. So what I'm going to do is I'm going to put the symbol for chlorine right here because I have to have that. And I'm going to put the 2 electrons in 1s here. 2 electrons in 2s. I don't have a red pen right in front of me, so they just have to know it won't write right now. So that's 2p here, 3s, and 3p. Okay, so actually I probably should turn these electrons in this direction. Let's do that here. Remember, there's 1 electron there. I'm sorry, 1 electron in this last box. So this box is going to be a combination of both. Okay? So I'm showing how this box, which had 1 electron from nitrogen and 1 electron from the chlorine, have overlapped. Well, to put it in the second box, I really kind of don't have room up here. I'm going to move it down this way. So let's put chlorine like this, and 1s, 2s, 2p, 3s, and 3p. So I've taken this same structure here with a box that only had 1 electron on the end. I put it here and I'm overlapping that last box, so I've got the chlorine and the nitrogen sharing electrons in that box. Okay, I need to get this last one. Now, for this last one, I could have the chlorines coming out this way. Just turn it upside down. Okay, let me put some red around this to show that's a combined one, and some red around this one to show I'm combining it. So I need to put, that's going to be my 3p. This is going to be 3s. This is going to be 2p. This is going to be 2s. This is going to be 1s. And here's chlorine with that colon. So the 2 electrons there and there. 1 in each box. Come back and pair them up. 2 electrons. 1, 2. Then I can put that 1 electron there and fill this up. Okay? So by doing this, I have shown how I might share electrons between chlorine and nitrogen using orbital notation. That's kind of complex. It's kind of tough to draw all that out. You just have to be creative. Okay. Now I need to do the same thing with the electron dots now. So with electron dots, nitrogen had 5 valence electrons. So in its outermost energy level, there were 2 here, and 1, 2, 3, and 2p, and that's 5 valence electrons. That's where we get the dots from. And each chlorine had 7 valence electrons. So in its highest energy level, 3s, 1, 2, 3, 4, 5, 6, 7, we want 7 dots. I can share here. Now the chlorine has 8 electrons, but nitrogen only has 6. I need another chlorine. Now chlorine, this chlorine has 8 electrons. Both these 2 chlorines have 8. But nitrogen only has 7, so I need 1 more chlorine to get the sharing arrangement. Now this, what I just drew here with this chlorine, that is an electron dot formula. What I'm doing here is showing the sharing arrangement, okay? So if we're labeling this, this is an electron dot formula, and then it becomes a sharing arrangement. And you can do it just one time. You don't have to draw out electron dots separately from the sharing arrangement. You can say this is the electron dot formula that became the sharing arrangement. Now from the sharing arrangement then, we're going to squeeze together electrons that are shared. So these two electrons that are shared get squeezed in between chlorine and nitrogen. These two electrons here get squeezed here. These two electrons here get squeezed here. And then all those lone pairs have to remain. And this is going to be a Lewis dot formula. Okay? Finally, we're going to have it. So if you're naming this, you're labeling it. This is a Lewis dot formula. And this is the Lewis formula where shared pairs and only shared pairs get replaced with lines. Shared pairs got replaced with a line. Shared pairs down here are going to be replaced with a line. But the lone pairs have to stay there. So that is a Lewis formula. So this is electron dot formulas. That became a sharing arrangement. This is a Lewis dot formula. And this is a Lewis formula. Now this is how you put together two nonmetals into a covalent compound using electron dots. This is how you put together two nonmetals using orbital notation. You can see how much complex this can get. This is a lot simpler, and this is what electron dots were originally created for. Okay, it's not hard to use orbital notation for ionic compounds, or these simple ones anyway. It does get kind of complex when you use polyatomic ions, but for this part of this unit, we're not going to be worried about ionic or polyatomic ions. Okay? All right, then the last thing you're supposed to know in this half of the unit is the three-dimensional shape of three different molecules. Okay? And for this class, we just memorized those. We had carbon dioxide. Carbon dioxide is a linear molecule. Just forms a straight line. Water is H2O. And so we've got an H bonded to an oxygen, and the angle between this bond and the next one to the second hydrogen here is at 109.5 degrees. Now you need to be careful. You don't want 120 degrees. You don't want 90 degrees. Okay? Let's see. Let me show you what 120 degrees. If this is A and this is B, this is 90 degrees. If this is A and this is B, 120 degrees is a little bit wider than that. It's almost off the paper over here. So we want 109.5 degrees. So don't get it too wide, don't get it too small. Okay, I'm not going to take out a protractor and measure it, but if it's a straight line, it's definitely not 109.5 degrees. If it's 90 degrees, it's definitely not 109.5 degrees. So somewhere reasonably wide, slightly less than 120, but slightly more than 90 would get you 109.5. Okay, so that's the shape of a water molecule. It's the shape of a carbon dioxide molecule. And what we need the next is the shape of a methane molecule. Methane, remember, has one carbon. Meth is the prefix for one. Ane is the suffix that means only single bonds between carbons. Each carbon has to have 4 bonds. And so if we only have one carbon, we need 4 hydrogens to have 4 bonds to that carbon. And a methane has what's called a tetrahedral shape. That's where you have one leg going up, one leg over here at 109.5 degrees, another leg at 109.5 degrees, but that one has to be swinging out toward you. It's like it's not flat on the paper, but it's swinging up like this, okay? and we represent that as a triangle. And then we've got one going back behind the paper. It's as if it's tilting back away from you, and we show that with a dotted line. So we just put the hydrogens on here now to show the shape of this molecule. This shape is called a tetrahedral. Okay, so this is a tetrahedral molecule. This is a linear molecule. And this is a bent molecule. Okay, so those are the three shapes that you have to know. And that's our pre-test review for the second part of the Unit 3, the test for the second part of Unit 3.